In this video, we'll discuss the properties of optical isomers such as optical rotation, optical activity, and optical purity. We'll explore the concept of polarimetry, define racemic mixtures, and examine the relative energies and physical and chemical properties of enantiomers versus diastereomers of the same compound. In the last video, we left off discussing the stereoisomers of tartaric acid, the enantiomers 2R3R and 2S3S tartaric acid, their diastereomer, the mesoform 2R3S or 2S3R tartaric acid. The enantiomers of tartaric acid, 2R3R and 2S3S, hold significant historical importance. In the mid-1800s, Louis Pasteur conducted a study on the recrystallization of tartarates, salts of the conjugate bases of tartaric acid, commonly found in wine. His research initially focused on a compound he named racemic acid, coming from the Latin word racemus, meaning a bunch of grapes. Plane polarized light, also known as linearly polarized light, is a wave of light that vibrates in a single plane, with all waves vibrating in the same direction. Unpolarized light from a light source is passed through a polarizer, which allows only light waves vibrating in a single linear plane to pass through. This setup is used in polarimetry, a technique that measures the rotation of plane polarized light as it passes through optically active substances. At the time, it was known that racemic acid did not rotate the plane of polarized light, while the most common tartrate rotated plane polarized light to the right. In his investigation of racemic acid, Pasteur discovered that it crystallized into two distinct crystal forms, which were mirror images of each other. By carefully separating these small crystals by hand, he observed that half were right-handed and the other half were left-handed. When dissolved in aqueous solution and exposed to plane polarized light, the solutions containing each type of crystal rotated the plane of polarized light in opposite directions by the same number of degrees. What Pasteur didn't realize at the time was that what he called racemic acid was not a single compound, but rather an equimolar 1-to-1 mixture of the enantiomers of tartaric acid. Upon recrystallization, the two enantiomers could be separated mechanically and their properties assessed. What we now know as the 2R3R enantiomer formed right-handed crystals and was dextrorotatory, labeled as plus, meaning it rotated plane polarized light to the right. Meanwhile, the 2S3S enantiomer formed left-handed crystals and was levorotatory, labeled as minus, rotating plane polarized light to the left by the same amount. A mixture containing only a single enantiomer is referred to as optically pure, since it results in full optical activity. Therefore, while individual enantiomers are optically active and rotate plane polarized light in opposite directions, a racemic mixture is optically inactive because the rotations cancel each other out, resulting in no net rotation. It's also important to recognize that the direction of optical rotation, whether dextrorotatory plus or levorotatory minus, is an experimental observation and is not directly related to the absolute configuration R or S of the molecule. As we discussed, molecules like plus tartaric acid and minus tartaric acid are enantiomers with opposite optical rotations, but their configurations R, R, and SS respectively do not predict these rotations. In practice, the only way to determine whether a molecule is dextrorotatory or levorotatory is to measure its optical rotation using polarimetry. This makes polarimetry an essential tool for distinguishing enantiomers and determining their optical properties in the lab. Apart from their difference in optical rotation, enantiomers have identical physical properties in achiral environments. For example, the enantiomers of tartaric acid, like any other chiral molecule, have the same melting points, boiling points, and solubility when in an achiral environment or dissolved in an achiral solvent. This is because in an achiral setting, the molecules are treated as structurally identical except for their handedness, which does not affect these physical constants. Additionally, enantiomers also share the same chemical properties in achiral environments, reacting at the same rate with achiral reagents. However, in a chiral environment, such as when interacting with another chiral molecule or being dissolved in a chiral solvent, both physical and chemical properties can change. This is because the spatial arrangement of atoms in the enantiomers allows them to interact differently with other chiral substances. For example, in a chiral solvent, one enantiomer may form stronger interactions with the solvent molecules than the other, leading to differences in solubility. Similarly, if a chiral catalyst or reagent is present, enantiomers can react at different rates or show different affinities, such as binding more strongly to a chiral catalyst. Conversely, diastereomers have different energies and physical and chemical properties, even in achiral environments. Unlike enantiomers, which are non-superimposable mirror images, diastereomers are not mirror images of each other and thus have different spatial arrangements of atoms. This difference leads to variations in melting points, boiling points, solubility, and other physical properties. Furthermore, diastereomers often exhibit different chemical reactivity, reacting at different rates with the same reagent or under the same conditions. Diastereomers can also rotate plane polarized light, but unlike enantiomers, their specific rotations are not equal and opposite. Each diastereomer has its own unique degree of optical rotation, which can vary significantly between diastereomers. These differences in optical rotation, along with their distinct physical and chemical properties, make diastereomers easier to separate than enantiomers, using techniques like fractional distillation or crystallization. As always, let's do some practice. Propose structures for A through G that are consistent with the experimental observations. Compounds A through C have the molecular formula C3H6O3. Infrared analysis of A and B reveals strong absorptions at 1740, along with weaker bands around 2720 and 2900, all indicative of an aldehyde RCHO functional group. Compound C, on the other hand, shows a strong absorption at 1718, consistent with a ketone RCOR functional group. Polarimetric analysis shows that A and B are optically active, rotating plane polarized light in equal but opposite directions, confirming that they are enantiomers. Upon treatment with Br2 under photochemical conditions, both A and B yield a single monobromination product, which can be resolved into enantiomers D and E. In contrast, C is optically inactive, and successive treatment with Br2 yields a single monobromination product, which can also be resolved into enantiomers F and G. Compounds D through G have the molecular formula C3H5O3Br. All compounds A through G show strong IR absorption at 3000, indicating the presence of an OH stretch, and showed negative results for the sodium bicarbonate test, indicating the absence of a carboxylic acid, COOH, functional group. Feel free to pause the video and try solving this problem on your own first. To solve the problem, we can start by analyzing the given molecular formula C3H6O3 for compounds A, B, and C. The infrared IR analysis of A and B tells us that both structures have an aldehyde group and at least one alcohol group. Since A and B are optically active and enantiomers, we know they must be chiral and mirror images of each other. The most likely structure for both A and B is glyceraldehyde, a 3-carbon molecule with one aldehyde group and a single chiral center. Therefore, A and B are either enantiomers of glyceraldehyde, D and L glyceraldehyde. For C, IR data tells us that there is a ketone functional group present and at least one alcohol group. Furthermore, polarimetry shows it is achiral. Given these observations, structure that best fits the descriptions for C is dihydroxyacetone, a symmetric 3-carbon ketone with 2 hydroxyl groups. Next, upon treatment with Br2 under photochemical conditions, A and B yield single monobromination products that can be resolved into enantiomers D and E. Bromination occurs at the asymmetric secondary carbon, C2, of glyceraldehyde. The radical intermediate leads to a non-stereoselective reaction, producing both enantiomers of the monobrominated glyceraldehyde, which are D and E. For C, bromination occurs at the same secondary carbon, C2, resulting in a product that can also be resolved into enantiomers F and G. Since dihydroxyacetone is symmetric, bromination creates a single product that generates enantiomers when resolved. The structures of F and G are the monobrominated forms of dihydroxyacetone. As always, thank you for watching, and I'll see you next time.